Professor Ray, please click on the Go Live button. Hello. Professor Ray? Yeah. Please click on the Go Live button.
So, good afternoon all, and welcome to session 4A, the future of IC engine technology and roadmap. I welcome you all to this session. Okay, sure.
Yeah. So, welcome everyone in the fourth session of this engineering track that is on the future of internal combustion engine technology and roadmap. So in this session we have two moderators. The first moderator is Professor Raja Banerjee. So Professor Raja Banerjee is a professor in the Department of Mechanical and Aerospace Engineering and the current Dean of Administration of IIT Hyderabad. He obtained his master's degree in cryogenic engineering from IIT Kharagpur and PhD in mechanical engineering from University of Missouri Road. His primary research interest is multi-phase flow, focusing on liquid spray and atomization, combustion of new and alternative fuel, turbulence, and parallel computing on COD application. Second moderator of this is Dr. Dhananjay Kumar Srivastava. Dr. Dhananjay Kumar Srivastava is currently working as an assistant professor in the Department of Mechanical Engineering at Indian Institute of Technology, Kharagpur. He did his PhD from IIT Kanpur. His area of research includes laser emission of SI engines, combustion visualization, emission control techniques, engine calibration, and gasoline direct injection technology. He has good research experience and he has published more than 30 international journal papers. With this brief introduction, I would like to hand over this session to the moderator, Professor Raja Banerjee.
Thank you, Dr. Ali, for your nice introduction. And welcome all to this session on future of IC engine technology and roadmap. As you all know that for the last 100 years, over 100 years, IC engine has been dominating the transportation and also the auxiliary power sector. But of late, a lot of questions are being asked about the future of IC engine. From our previous sessions, we have also realized that the alternatives to IC engine, they themselves have challenges. So keeping that context in mind, we will look at what are the future scope in IC engine research and its application. And we have 6 panelists of vast experience and eminence. So we'll first start with Professor Gautam Kakati, who's the consultant professor at Shanghai Jiaotong University. So, Professor Kakati, can you please start your presentation? And I will also request all the panelists to keep their presentation within 10 minutes, and around 8 minutes I will bring you so that you can wind up. Thank you.
Good afternoon, ladies and gentlemen, and thank you, Professor Banerjee, for inviting. I think I'll turn my camera off. It's not very good at the moment here. So anyway, right, thank you.
Professor Banerjee, could you please switch off your camera, then the bandwidth will be better at the presentation.
Right. Okay. And you're going to show my slides now, please. Right. Okay, thank you. As Professor Banerjee just said, I mean, there is a lot of people in the world who think that the internal combustion engine is dead. I mean, in fact, it will be completely replaced by battery electric vehicles. And well, I'm going to argue, as I think you've already heard from many, many people in session 3A and so on, that this is not going to happen. It's not the end of the internal combustion engine. And in the next few slides, I'll try to make a case for this, okay? Now, global transport accounts for about 23% of CO2 emissions. Global CO2 emissions, 20% of energy use. And if you take into account methane and nitrous oxide and things like that, it's only about 14% of global greenhouse gas emissions, which is the same share as the whole of livestock farming, in fact. There are around 1.2 billion light-duty vehicles, cars and vans, and over 350 million commercial vehicles in the world. Okay, and these are increasing mostly in non-OECD countries, and they're expected to go up to between 1.7 and 2 billion light-duty vehicles by 2040. However, LDVs account for only 44% of global transport energy demand. I'm giving you all these figures just to give you an idea of how big the sector is and what the scale of the challenge is. And transport, as you know, is essentially driven by liquid fuels because of their high energy density and so on. And every day of the world uses about 4.9 billion liters each of gasoline and diesel, and about 1.2 billion liters of jet fuel. That is 11 billion liters of liquid fuels every day. We have to remember this when we talk about alternative fuels and so on, you know. And demand for transport energy is growing mostly in non-OECD countries. And as you know, petroleum, that's oil, and transport are closely linked. 95% of transport energy comes from oil-based liquid fuels. And 60% of petroleum goes to make transport fuels. Next slide, please. Now, I would like to focus a little bit on electric vehicles. As you know, there are different degrees of electrification. And of all these, only full battery electric vehicles do not have an internal combustion engine, and all their energy comes from the electricity grid. And there are, of course, in between vehicles like hybrid electric vehicles like the Toyota Prius, which have a small battery. However, all their power and energy comes from the internal combustion engine. But electrification makes the whole process more efficient. And we also have plug-in hybrid electric vehicles, but plug-in hybrid electric vehicles also have an internal combustion engine. And in fact, so if you want to eliminate internal combustion engines, you have to replace all the cars by battery electric vehicles, essentially. Of course, we know that hybrid electric vehicles are the most practical and proven technology, and they're currently available, and they can reduce fuel consumption in gasoline light-duty vehicles. Next slide, please. Now, battery electric vehicles numbers are increasing fast. There's no question about it, because they start from a very low base. And by the end of August 2021, the world had about 6.5 million. In fact, now they say there are about 7 million battery electric vehicles in the world, which is still about 0.5% of the total number of light-duty vehicles. But another thing you have to remember is that battery electric vehicles are not really relevant for heavy-duty, long-distance road transport, shipping, and in fact, it's impossible for aviation. So even if you replaced all cars, LDVs by battery electric vehicles, you would still address only about 44-45% of global transport energy demand. We have to remember this. However, such a massive increase in BEVs will have unsustainable environmental and economic impacts. Next slide, please. What we have to remember, and the governments have to remember, which they conveniently forget, are BEVs are not zero emission vehicles. The greenhouse gas impact depends on how electricity used is generated. For example, in India, a BEV will cause more CO2 in most places in India because electricity generated from from coal mostly. And of course, if on a life cycle basis, battery production is very energy and CO2 intensive. And if you take all this into account, for example, a recent study we have completed with Professor Agarwal's group and so on, in India, four-wheelers with even modest size batteries will actually increase greenhouse gas emissions. Two-wheelers will be better than the equivalent petrol ones because they have very small batteries, and therefore the embedded energy CO2 in the battery production is very small. But these are extremely expensive still. I mean, most people who buy two-wheelers probably cannot afford to buy them, actually, even with existing subsidies. And of course, other emissions like particulates and NOx and SO2 will also be worse if coal is the source of power. And similarly, human toxicity potential associated with mining. And so what you're doing is you're basically exporting the health impacts of battery electric vehicles somewhere else where they are not used, essentially. And in fact, once in the future, internal combustion engines become very clean, because especially if they have particulate filters, the main source of particulates will be from tire wear. And in that case, battery electric vehicles will have higher particulate emissions because of the greater weight. So essentially, on a life cycle basis, BEVs are not necessarily green or clean. Well, I call them emissions elsewhere vehicles, EEVs. Okay, next slide, please. Of course, I won't go into all these other economic and other implications of forced electrification of light-duty vehicles, like cost, incentives to persuade motorists to buy them, cost and availability of extra electricity needed, and the changes in infrastructure that is needed, problems and costs of recycling the batteries, availability of materials to replace all LDVs. This is a very, very serious issue. Remember, if you want to replace all LDVs with BEVs, you have to increase the number by a factor of maybe 200, a factor of 200. And this is going to make it very difficult to get the materials required. And in fact, this is already showing up. The cost of lithium is really doubling almost every year, and there are other issues associated with mining of metals and so on as well. Next slide, please. So what is to be done to reduce impacts of transport? This is the point, we have to recognize the scale of the challenge required honestly. For example, aviation cannot be truly decarbonized. If you want to decarbonize aviation for all practical purposes, you have to shut it down. And you have to assess the impacts honestly on a life cycle basis, and recognize that alternatives, BEVs and new fuels, start from a very low base and face huge environmental and economic barriers to quick and unlimited growth. Of course, there is significant scope to reduce energy use in ICVs, in other words, improve its efficiency, for example, with partial electrification like hybridization and so on. And there are other possibilities to using legislation to discourage travel, increase taxes on big cars, and so on. I mean, but these are beyond the scope of this talk, basically. Important thing to remember is we have to sensibly deploy and continuously improve all available technologies. BEVs cannot, and in fact must not, for environmental other reasons, completely. Okay. Thank you. That's it.
Thank you.
Thank you. There are various publications there. If anybody is interested, they can look them up.
Sure. So what we do is we have all the panelists go through the presentation, and then on the question answers we'll take in the panel discussion. So now the next presentation is by Professor Pankaj Kole. He is my colleague at the Department of Mechanical and Aerospace Engineering at IIT Hyderabad. So, Pankaj Kole, please.
Good afternoon, everyone. Good afternoon. I'll be delivering a seminar on renewable fuels, fuel blends as drop-in fuel for IC engines, promoting essentially the carbon recycle with maximum utilization of renewable fuel. The outline of my talk would be as follows. I'll start with introduction, then discuss the two case studies. The first case study demonstrates the 60% renewable fuel utilization in PFI engine on a thermal blend that will involve the lemon peel oil, ethanol, and gasoline. The second case study basically is related to the atomization disturbance, which is basically going to aid in injection strategy and mixture preparation. Okay, and finally I will summarize. Okay, coming to introduction. So in today's era where we are promoting the electrical vehicles, the question is why continue R&D efforts in IC engines? Okay, so existing infrastructure and employment, the repair and maintenance industries associated with the piston engines provide strong incentive to remain with this technology. Okay. There is no immediate shortage of hydrocarbon fuels in near future. With rise of biofuel research, methane chloride hydrates, isoprene capture for plants have provided the motivation to continue research in IC engines. The only question that is remaining here is increasing the efficiency and emissions, reduction of the emissions that is there. Okay. With the advent of fuel reforming, the hydrocarbon fuels are not seen to be significantly different from each other. Okay, the onward fuel reforming concept has opened the opportunity to develop engines that can operate on multiple fuels, although this has not been pursued strongly in India. Okay. Now, the renewable fuels and carbon recycling basically becomes one of the avenues to sort of address the issues of dirtier IC engines, right? So, usage of renewable fuel helps address the typical notion of dirty IC engines. Due to the carbon recycle and supplanting the conventional fossil fuel is possible. Renewable fuel, basically, whenever you are dealing with the renewable fuels, the combustion and thermophysical properties play a role in utilization percentage of the renewable fuels. So we are focused on that. What is basically a typical drop-in fuel will be. For drop-in fuel, you would need to basically match the thermophysical properties as well as the combustion properties. Okay. What we research to have focused on for a drop-in fuel is the limited impact on vehicle range, which is a problem for electric vehicle powertrains, and also from implementation perspective, the drivability, that is the coefficient of variation should be limited to 10% and needs to be looked into. Okay. Now, recent trend of elimination of smaller size diesel engine passenger vehicles from the BS6 norms perspective, a test case for SI engine is considered, and we are seeing that there are multiple alternative fuels available for the CI engines, but very limited fuels are available for SI engines. So I have taken here the cases for the SI engines. Okay, so coming to the first test case where PFI engine performance is shown on ternary blend involving the lemon peel oil, the ethanol, and gasoline. And these are the typical basically properties those are comparing. Here the lemon peel oil is essentially produced by the steam distillation of lemon based lines, and you can see that mainly it is the so mainly it is the C10 H16 and very little basically fraction of the fuel mount oxygen is there. If you look into the properties, the calorific value as well as the stoichiometric air fuel ratio are very comparable to the gasoline, and it has got acceptable octane number number rating also. And in case of the terminal blend, we could always use the ethanol as the basically the octane number improvement perspective. Okay, now the blend properties from perspective of heat addition per unit mass in cylinder for drop-in fuel perspective deviation within the limit of 5% is considered here, because we were looking into keeping the vehicle range same as well as having the coefficient of variation less than 10%. We all know that if you go with the ethanol, increasing the ethanol percentage beyond 20% leads to the coefficient of variation greater than 10%. Okay, so there are restrictions when basically you deal with the other alternative fuels. Okay, now this doesn't mean that we try to ensure that heat addition per unit mass in the cylinder, okay, with respect to the conventional fuel and the renewable fuel blend, okay, that limits to the plus minus 5%, but that doesn't mean that the kinetics is the same. Okay, but what we expect is the limit of growing discrepancy, because we always know that heat release per unit vesicle mass would control your temperatures, and Arrhenius law will basically play a role in reaction rate kinetics, and the discrepancy would be limited. Okay, if we try to maintain that. Okay, so we already know that the peak pressure based combustion phasing is observed to be advanced for this ternary blend, because both LPO, that is level oil, as well as the ethanol has higher fuel speeds compared to gasoline. Okay. Now here, if you look into the nomenclature, the alphabets G, E, and L refers to the gasoline, ethanol, and lemon peel oil, and the numbers basically indicate the volumetric fraction used in the blend. Okay. If you look into the last one, G40, E20, L40, okay, you will see that very comparable air to stoichiometric air to fuel ratio with the gasoline, pure gasoline is there, as well as the heat added per unit volume inside the cylinder is very comparable. It's less than 1% deviation with the pure gasoline. Okay, so note that here basically I have used this stoichiometric air to fuel ratio because most of the SI engines are operating about the stoichiometric air to fuel ratio. Okay, from the brevity perspective, I have only basically presented the salient results on this particular slide to demonstrate how basically we utilize the 60% of the renewable fuel, okay, in SI engines. So 10% EGR, G40, E20, and L40 shows overall improvement in performance emissions over baseline pure gasoline. So all basically, test cases here are shown with the 10% EGR, and with respect to the baseline gasoline without any EGR, the performance is basically shown. Here you are seeing the PSFC, here you are seeing the brake thermal efficiency, CO, SC, and NOx emissions. Okay, the red one is basically showing you the G40, E20, and L40. Okay, so emissions are improved over the pure gasoline, as well as the brake thermal efficiency is also improved, and very marginal, close to 4% increase in PSFC is observed. That's because we are basically have to deal with the utilization of 10% EGR to bring this NOx down compared to the baseline gasoline. So we can basically say that G40, E20, and L40 is basically going to give you overall improvement in the performance over baseline gasoline with 60% utilization of renewable fuel. Okay. So coming to the next test case, which is essentially the spray characterization perspective on alternative fuels for GDI engines. For liquid fuel combustion, atomization plays an important role in mixture preparation, and thermophysical properties of renewable fuel impact spray formation. For this, we have basically utilized the constant volume chamber, okay, for the spray diagnostics and the PDP measurement campaign. Okay, what is basically done is the ambient conditions are basically
Here, 2 minutes.
okay. What is done is the ambient conditions are basically changed with respect to the that basically simulates the pressure temperature conditions for 30-degree BTDC, 60-degree BTDC, and 90-degree BTDC crank angle. So the pressures and the temperatures are somewhere like 1.5 bar 329 Kelvin, 2.5 bar 371 Kelvin, 6 bars 450 Kelvin. So if you look into the boiling point, okay, so we are basically looking at the isooctane and LPO comparison, like non-evaporating sprays and near evaporating sprays. Okay, so here basically I am also again from the perspective of brevity, I am just presenting the salient results here, and you are basically seeing here the isooctane and lemon peel oil cumulative volume fraction for the first situation. Okay, so 1 bar and 298 Kelvin. So both of these basically sprays are non-evaporating sprays. Then isooctane basically goes close to the near evaporating with the comparison of non-evaporating LPO sprays. Then you have got evaporating isooctane and near evaporating LPO spray here. Okay, so if you basically look into the perspective, say, okay. So you compare like this as 17 SMD micron, basically the droplet size. What is the cumulative volume fraction is indicating that the LPO is atomizing the chunk of liquid fuel only close to the 45% below say 17 micron droplet size. All rest basically is close to above the 17 micron droplet size. Okay, and for isooctane you are basically seeing it's nearly close to the 80%. Basically atomization perspective. So that basically leads to the conclusion slide. So we have demonstrated 60% utilization of renewable fuel. Then matching the combustion and thermophysical properties basically enables maximum utilization of essentially the renewable fuel. And for 100% renewable fuel, intricate thermal management for fuel delivery and EGR would need to be looked into. And considering the roadmap for the future, looking into the variable compression ratio of post-piston engines for full reliance on the renewable basically fuels may need to improve the thermal efficiencies compared to the alternate powertrain. With that, I'll finish my presentation.
Thank you, Pankaj. Next, we have Professor Chun Bin from Department of Mechanical Engineering of Korean Advanced Institute of Science and Technology. Professor Bin, please start your presentation.
Okay, thank you. Shall I share my presentation material or will you upload it?
Yeah, they are uploading.
Okay, thank you. It's my honor to talk in this conference. My talk is about the e-fuel application for automotive power plant, which is a general overview on the e-fuel usage. Next, please. This is an ideal green transport power scenario where the energy resources are renewable energy, electricity, nuclear power generation, and biomass. With these green energies, we could use battery electrical vehicle, fuel cell electrical vehicle, hydrogen internal combustion engine vehicle, and renewable fuel internal combustion engine vehicle together with the hybridized type. Here the renewable fuels include the synthetic electric power-based e-fuel and biofuels. Next, please. This e-fuel is a synthetic carbon-neutral fuel which is made by the recycling of CO2. Even though internal combustion engine emits CO2, this is captured and then combined with hydrogen to produce e-fuel. The hydrogen is produced through the electrolysis, utilizing the electricity made from renewable energy resources. So this cycle makes the carbon neutrality. Next, please. This is a type of ideal e-fuel production. CO2 is captured from the ambient air, and the green hydrogen is combined through this Fischer-Tropsch process to make a high degree of hydrocarbon fuels compatible to gasoline and diesel and so on. So this kind of liquid fuel production utilizing CO2 serves CO2 reduction. Next, please. E-fuel is a product of CCU technology, which is carbon capture and utilization. Starting from the basic e-fuel, hydrogen, the spectrum of e-fuel covers all different kinds of hydrocarbons such as e-gasoline, e-diesel, e-LPG, e-jet fuel, e-methane, e-DME, e-methanol, e-ammonia, etc. Especially e-methanol and e-ammonia are regarded as very effective liquid energy carriers which can compensate the lack of renewable energy in most advanced countries. So this e-methanol and e-ammonia could be traded globally to make the balance and suffice the need of energy, and the e-fuel is desperately needed for the high energy and power density transportation field, which was already mentioned by Dr. Gautam Khalgaki, and I found yesterday in the session 1A in fuels, this kind of e-fuel production and application and the feasibility were already touched. I appreciate the comprehensive contents of 1A session. Next, please. One big challenge for the e-fuel is the efficiency issue. Compared to battery electrical vehicle, the internal combustion engine vehicle utilizing e-fuel has very low efficiency under the condition that all the energy resources are from renewable energies. Still, we should improve the efficiency by maximizing the use of hybrid powertrain. The efficiency of this is still the half of battery electrical vehicle, but definitely still you need this kind of fuel for high energy density and high power density transportation tools, such as aviation, marine, and heavy-duty on-road vehicles. Next, please. This is an example of heavy-duty vehicle case. This is the field where the battery electrical powertrain could not be implemented. The efficiency of e-fuel is still just half of conventional diesel powertrain. Next, please. However, in case of marine application, the level of efficiency of internal combustion engine is similar or higher than the battery electrical vehicle. Next, please. The very basic e-fuel is the hydrogen, and we are trying to achieve the carbonless combustion operation. This hydrogen combustion would be a perfect carbon neutral solution as long as NOx emission is reduced or removed somehow. Next, please. We are trying to realize the hydrogen internal combustion engine by optimizing the lean stratified charge combustion. This optimal design could be done by the observation of hydrogen jet and mixture formation followed by ignition and flame propagation. Next, please. This is from the literatures. The e-gasoline shows the possibility of highly efficient operation owing to its high compression ratio, utilizing the high octane number fuel, which is paraffinic. And the e-diesels without polyaromatic hydrocarbons can achieve the soot-less combustion as well. Next, please. Let me summarize by rephrasing the benefit and the visions of e-fuel. It is effective to import liquid energy carriers by applying power-to-liquid technology, which has a high energy density. Liquid fuels are economical for storage and transportation, while renewable energy resource is not enough in most countries. E-fuel is part of carbon capture and utilization technology that actively utilizes and reduces carbon dioxide and essential as a transport power fuel with high power and energy density. Large commercial vehicles are expected to develop technology with the adoption of e-fuel. The non-soot internal combustion engine might be realized by the non-aromatic e-diesel fuel, and high compression ratio spark ignition engine allows high efficiency with high octane number e-gasoline. Energy conversion efficiency could be improved with the emission reduction through the hybrid system, while most internal combustion engine vehicles for passenger cars are expected to be hybridized by 2040. Engine efficiency improvement, hybridization, and clean fuel switching to e-fuel play an important role in carbon reduction in transportation sector during the transition period and eventually carbon neutral era someday. Thank you very much. That's it from me.
Thank you, Professor Bay, for your very interesting presentation. And next, we have Professor Rasheed from Department of Mechanical Engineering, IIT Bhopal. Professor Maurya, the floor is yours. Can you please unmute yourself?
Yeah, sir, can you please share my presentation?
Yeah, can you start?
Yeah, okay. I'm not able to see the presentation on this full screen.
Can you see now your presentation?
Yes. Now it is.
Okay.
Yeah, okay. Good afternoon to all of you. And it is my pleasure to share some of my thoughts. And I will be talking very briefly overview of this role of low temperature combustion engines in future powertrain for sustainable transportation. So next slide, please. Yeah, so this is a just trend of transportation sector and the fuel consumption, and Professor Kalgatgi has presented a lot more data on this one. So this just I wanted to show that the number of vehicles are anyway by increasing, and it is mainly because of the population increase in China and India, and there are developing economies. So the basic idea is that road transportation will be dependent on the fuel powered vehicle. So that is the basic motivation for this slide, and Professor Gargi has presented a lot more data on this. So next slide, please. So this I have just summarized the uh, possible challenges in the transportation sector and what are the possible options for this one. So first is the increasing the population and wealth will lead to change in the transportation and rapid increase in the fleet demands. So this will include the challenges of energy security concern for any particular country or the state, and then the overall greenhouse gas emissions, worsening the local air quality because of this burning of fossil fuels that we already know, and several governments are trying to implement various decisions on this. And then there are customer demands, because increasing these things, there are the customer demands are also something like people want to use SUVs and more torque or power, and these kind of demands are there. So these are the challenges, and based on these challenges, there are several options that are available. Ones such as battery electric vehicle, fuel cell based electric vehicle, hybrid vehicles, maybe alternative fuels or alternative combustion engines based vehicles. So there are many alternative fuels like alcohol, natural gas, and all those things are there. So in all of these there are critical obstacles for implementing this. So some of these obstacles are already discussed by Professor Kalgadgi regarding this battery electric vehicle, based on the availability of raw material, economic, and several other aspects. So one such is the lack of infrastructure, because if we want to implement either battery electric vehicle or fuel cell, or even with the alternative fuels also, in every country, this like in our country also, like the CNG, even CNG infrastructure is not available in all the cities or maybe in all the states. So even for alternative fuels such as alcohols or other things, this infrastructure development is required. And if you are planning for electrification or maybe a hybrid electric or electric vehicle, then also this infrastructure will play an important role in implementation. The other point is the life cycle analysis with respect to all this battery electric vehicle or fuel cell based vehicles. So we need to do, because sometimes if we, as Professor Kalgatki also said, that if we hybridize, let us say, or if we run all the vehicles on battery electric vehicle, then maybe will be emitting more carbon dioxides. There are government regulation and policies. So based on that, in every country, we have to choose the best options. And then there are innovative technologies are coming up, like e-fuels and other things, and then rare earth metals, there are toxicity involved. So all these options have their own pros and cons. So we have to judiciously choose which options will serve and with respect to a particular challenge in the transportation sector. So the engine summary, even by 2040, the share of mentioned these possible options will not be more than 10%. So mainly for several decades, the vehicle will be powered by internal combustion engine. So as Professor Kagati has said, it is not the end, and it is discussed in several other sessions also. So it means that we have to improve and do research in internal combustion engine. So next slide, please. So for internal combustion engines, we can either, there are two options. So one major is that either we improve our conventional internal combustion engines and conventional fuels. So by improving this conventional engines and fuels, we may achieve some of these challenges. But the other route is utilizing the alternative combustion modes and alternative fuels. So for alternative fuels, maybe Professor Kole has said, and Professor Bay also has discussed few things. So the alternative fuel is one option. Then other is the alternative combustion strategies. So there are several, over the period, there are several strategies that are developed for alternative combustion modes. So if we are trying to find a optimal solution or a in general solution, then we can either choose alternative combustion, alternative fuels, or improving the combustion conventional things, or maybe combination of this, like the alternative fuels in alternative combustion modes also. So these things can be there. So this slide basically just shows the evolution of different low temperature combustion strategies. So basically the basic one is the premixed combustion, that is called homogeneous charge compression ignition engine, and the concept is developed and tested and demonstrated by several universities and several researchers in maybe the late 90s or so. So, but in this kind of combustion, we demonstrated that it has potential of high efficiency and ultra low NOx and particulate emissions. But there are challenges related to combustion control and maybe the maximum load range where we can go. So then it was thought that maybe we can go not in a purely homogeneous premixed combustion mode, maybe slight stratification. So with respect to for stratification, there are thermal stratification, and then there are fuel stratification. So with respect to fuel stratification, or maybe slight partially premixed or charge combustion. So there are diesel partially premixed combustion PCCI, or partially premixed combustion PPC for gasoline, and there are gasoline combustion ignition engines. So these technologies are developed and demonstrated, and they have shown promising result with respect to high efficiency and lower NOx and particulate emission. And then to improve the combustion control, then in addition to fuel stratification or equivalence ratio stratification, reactivity stratification is also proposed by using two fuels. One is high reactivity fuel and other one is low reactivity fuel. So that is called reactivity control compression ignition engines. So these is the evolution, and people are working on it, and every year we are getting new results. So this is the basic overview of this low temperature combustion technologies. And this low temperature combustion means it is well below the temperature limit of NOx formation and this soot formation that can be seen in this graph of operating range of various low temperature combustion strategies. So this is just an overview. Next slide, please. So based on this, I have just tried to summarize the aspects of the IC engine research. So we have to improve the efficiency and reduce the emission. For this, the combustion control and after treatment system, like the low temperature after treatment systems, are required. So gasoline particulate filter and these things are coming up because of gasoline direct injection and all. So with respect to this, maybe we have to work on alternative fuels, so that like low octane fuel like naphtha for gasoline combustion ignition kind of modes, and high carbon fuel, alcohol, maybe slightly butanol, it has better mixing characteristics. And these are some of the things related to alternative combustion regimes. So like HCCI, RCCI and all. There are many challenges. Cold
You have a minute to continue, yes, please.
Yeah, so next slide, please. So this is just an option that this low temperature combustion vehicles can be used for hybridization, and it may work better because it has better efficiency at lower engine loads also. So next slide, please. Just one. So from this, I just wanted to emphasize that for several decades, that powered by internal combustion engine, global transport is dependent on fossil fuels, and we have to work in development of clean alternative fuels and alternative combustion mode, and hybridization with advanced combustion modes such as RCCI will be possible. And the future transport will rely on various government regulation policies with respect to infrastructure, emission regulation, and the production related issues with refineries. And it also depends on consumer behavior, perception, and choices. For this will lead to the future of the transportation sector. Thank you all.
Thank you, Professor Modi, for a very interesting presentation. So now the next speaker is Professor Antonio Garcia. He's from the Department of Thermal and Reciprocal Intelligence of the University of Public at Valencia. Professor Garcia, can you please start your presentation?
Yeah, sure. So I see that you prefer that you are going to control it, okay? Okay, so maybe you can put in presentation mode. Okay, so thank you so much for inviting me to be here. It's an honor. So I would like to say thank you to all the organizations. So it's really interesting Congress, and I have been attending past day presentation. So with really high quality. So from my side, I'm going to try to talk about internal combustion engine role under new regulation that is going to appear for European sector. So next slide. Okay, so the outline of the thing that I'm going to explain, so it's related with, no, you can go to slide number 3, no problem. Next slide, yeah. Okay, so here you have a picture of the European CO2 emission, in which, so you have the annual total CO2 emissions by global regions. So there you can see in different colors, so European Union, it's something like, you can click, please, in order to put the animation. Can you click? So to put the animation, so you can go to all the animations on this slide, sorry. So one click more, one more, okay, up to there. No, so just slide number, slide number 3, okay. Well, the thing that you can realize here is that we have a huge increase in the CO2 emissions, but those regions in which we have are the more dominant production members in terms of CO2, like it can be China, for instance, or Asia, excluding China and India. Well, I mean, if we go to European road transportation, so we have something like 18% of the total CO2 in Europe. So if you go in details for each one of the different sectors, so you can realize that heavy duty, it's around 25%. So medium duty, it's something like 12%, and for sure passenger cars is around 60%, and the bikes are something that are quite almost negligible. So this means that in terms of the European Union, so we have 80% of something like it's representing 90.8% of the total amount of CO2 in the world. So we are discussing in Europe about 1.7% of the world CO2 emissions. So I mean, it's quite a small number. So maybe you can go next slide. The idea is how the European Union is planning to reduce this 1.7% of CO2. So next slide. So you can make all the animations for this slide. So one more. Okay, that's it. Well, so if you take which are the recent movements of the European Union, so you can see that from 2019 we have started with Green Deal. So this means that the non-net emissions from greenhouse gases are needed to have in 2050. So in 2020, Euro 7, like a regulation, is something that has to start sounding very hard. But even still now, it's not in the street. So the Euro 7, the thing that is focusing is in accelerating the shift to sustainable and smart mobility. And finally, in June 2021, has appeared Fit for 55, in which it's said that at least the 50% of the emissions of the ones that we have right now needs to be reduced by 2030, as well as all new cars registered by 2035 will be zero in terms of tailpipe emissions. So this means or electrical vehicles or hydrogen or ammonia. But if you think on that, this is not needed to mean that we are going to ban all the internal combustion engines in Europe. So because they can be even cleaner than electrical vehicles, the internal combustion one. So maybe next slide. Okay, so is the electric vehicle ready to take up this role now? So you can click, okay. So we have some challenges for electrification. So from both sides, external challenges as well as internal challenges. So some of them has been talked by previous speakers. So we have infrastructure, energy increase, recycling, raw materials, clean energy, asset politics. So from external point of view, from internal point of view, so we have the aging of the batteries, the energy density, the temperature, thermal runaway, autonomy, higher weight that you have with an electrical vehicle. So I mean, what is clear is that it's not going to be tomorrow when everything can be in Europe with electrical vehicles. We have a lot of challenges that need to be solved, and then we have a huge transition period. So next slide. Okay, how the internal combustion engine can be an alternative on this. So next slide. Okay, from the left to the right, you have the CO2 emissions in terms of passenger cars in megatons of CO2. So, and then you have a temporal evolution. So gray color, you have the historical series. So in gray color dotted line, you have which will be the point in which we are going to arrive following the 2030 regulations. And also in dotted blue color, you have which is going to be the European Green Deal. Following the European Green Deal, how we are going to arrive. So this means that we have kind of 3.7 gigatons of CO2 that we need to reduce. So, and then we have two scenarios. So the first scenario is one in which the internal combustion engine is banned. So by using 2050 mix, or what is supposed to be electricity mix. So this means 10% of internal combustion engines, 90% of electrical vehicles. So maybe you can make the animation, please click. So, and then we have the other scenario. Sorry, can you go back? Yeah. So maybe, so you have this second scenario in which we have, almost 70% of the cars can be with internal combustion engines, but later we have electrification. So something like 16 being a pure electrical vehicle and the rest or plug-ins or full hybrid. So the idea here is that low carbon and renewable fuels can be a more direct solutions with low infrastructure requirements. So next slide. So, well, from the left to the right, you have how it can be a pathway to decarbonize the transport. So we can have CO2 savings in light duty and also in heavy duty. So in the left hand side, or let me say in the left side, so you have the CO2 equivalent for a comparison of the Kia Niro, in which you have a full hybrid vehicle or plug-in or directly battery electrical vehicle. So with different colors in bars, you can see which is the CO2 that we are procuring by using, how to say, the manufacturing of the car, the battery, the fuel, the electricity, and the end of life. So just taking a look on this graph for the Kia Niro, so that is exactly the same vehicle, you can realize that by using, for instance, hydrogenated vegetable oil, so you are going to achieve really, really nice CO2 equivalent runs per kilometer compared with electrical vehicles, by even in the case that you are using an electricity mix from 2050. So it's quite similar in the right-hand side when you compare the electrical vehicle in terms of a heavy duty. So when you compare that technology versus the ones that you can obtain with an internal combustion engine vehicle, also by using hydrogenated vegetable oil. So we are, how to say, quite comparable technologies. So can you go for next slide? Okay, so this is quite interesting. This is quite interesting because this is something that Professor Bai has raised. So it's you can see which is the losses per value chain that you have in the left hand side of the slide, resulting of the total mobility efficiency. So this is something that a lot of how to say, internal combustion engine haters are claiming for. I'm not saying that Professor Bai is one of them. So it's just saying that here, if you see that, so you can relate, for instance, for Germany. So you can say, okay, an internal combustion engine by using fuel, so it has a total efficiency of 30% or 13%. So if you compare it with an electrical vehicle that is using electricity also procured in Germany, so you're having a 70%. So for sure, this is only comparing, how to say, directly. What's up if we compare concerning or considering the location of the energy generation? Okay. So well, if you click in the animation. Can you click? Okay. So here you see the scenario in which we can compare the different places in which the energy is related or is produced. So, and then which is the efficiency of procuring that energy. So if you take a look, maybe you can make a click. Okay, so you can compare that dependently on the wind or the solar energy. So if you compare, for instance, Germany versus Morocco or Algeria or even Chile, so you can realize that we are having the third of the efficiency procuring this green electricity, because you should remember that for electrical vehicles may make sense in terms of CO2 if they are using green electricity. Okay, so can you click? Can you make the animation? Okay, so then if you compare, for instance, so in the left-hand side, so you have the previous scenario, and on the right-hand side, so you have, which is the scenario right now, in which we can compare this 40%, so this 13% of internal combustion engine vehicle efficiency that is used, green electricity that is coming from Morocco, or if we compare that with something that is used an electrical vehicle, so by using the green electricity that is procured or produced in Germany. So there you can compare.
Professor Garcia, you have about a minute to conclude.
Okay. So there you have only 1% of difference. So what I want to highlight here is that with an holistic approach of where the electricity is produced or the e-fuel is produced, it's super important in order to make direct comparisons. Okay, maybe you can go next slide. So and then we have the takeaways. So maybe you can click again. Okay. So here you have the different decarbonization ambitions in the transport. So just to say, the electrification needs to have, it's not really for today or for tomorrow. So it has a transition. So and then low carbon fuels need to be deployed in order to achieve carbon neutrality. So there you have to take advantage of the infrastructure. And you can apply, as other speakers have said, to other applications. So maybe you can go next slide. Okay, so and this is something that you should have also in your mind. So we need cleaner fuels also for cleaner engines, and this is part of the solution. So me, myself, like European, so you can see that we are going to be, in fact, the first continent in which we have carbon neutrality for 2050, but I don't know exactly which is going to be the counterpart, or which is going to be the different problems that we are going to attain in terms of where we are going to appear in the rest of the world. And if you click one more, I would like to say, everyone, thank you for your kind attention, and for sure later, I'm absolutely open to discuss whatever you wish. Okay, thank you so much.
Thank you, Professor. So the last presentation in this session is the presentation of Professor Mayank. He is the Department of Mechanical Engineering, IIT Madras.
Yeah, good afternoon, everyone. Thank you, Professor Nagar. It's a pleasure to be here. I'm Mayank Mittal. I broadly work in engines, primarily in laser based diagnostics engines and gaseous fuel engines, and more recently we are working in motor gas control and hybrid powertrains also. So, in the theme of the society, I think I have brought the title for today is utilization of bioresources as a system energy source for gaseous fuel internal combustion engines. And the talk will include some energy scenario globally, and then how this is split in renewable and non-renewable sources. and then I will talk about biofuel aspects, and then we'll focus on biogas in particular, and a couple of slides to addressing some limitations for future perspectives. Okay, so if we see this global energy scenario, we see that as we all know that the total energy consumption is growing with every year, and of course in 2020 it was relatively lower than 19, particularly due to the pandemic situation. But we ignore that there is quite a significant increase in the total energy consumption in developing nations like particularly we see like continents in Asia, Africa, and Middle East from the last 20 years. As you could see, these graphs growing quite significantly. So, of course, there is a need of more energy consumption there. Then the concern, of course, as we all know, is CO2 emission, and this is the slide that gives the information about the years, and you could see that particularly China, India, and Japan growing with time and contributing to a large extent now, particularly China. So there is definitely a concern, and as we have seen in COP26 meeting, some net zero targets for different nations by 2050, 2060. We are also committed for 2070 now. So if we see like the share of energy in terms of renewable and non-renewable, still we have a significant share based on non-renewable generation, which is about 75%, 74% here, and then you see 26% which is coming from renewable, and which is also primarily because of the hydro, wind, and solar here, and the bio share is only 2.2%. So there is a significant potential to boost energy supplies, particularly in populous nations with rising demand, such as India, China, and Brazil. And this can be used to produce the transportation fuels for heat and electricity generation, as discussed by other panelists. This is going to be very important in the future, and I'm not talking about the hydrogen and hydrogen carriers in this presentation, which is already been covered. So biomass is expected to double globally by 2022 as compared to 2012. So it's going to play a more and more important role. And the government of India has also raised its target for the renewable energy share. India has high potential to generate 28 gigawatt of bioenergy with annual biomass availability of around 750 million metric tons. And we have certain schemes that are going on now to promote this biomass-based bioenergy, which could be come like through animal manure, crops, food waste, and generating through the biowaste. The main advantage is eliminating the methane emissions and reducing the carbon dioxide emissions. So it can be then used for power generation, or it can be further upgraded to get to the biomethane, and then can be used for transportation purposes. So coming to the biogas fueled IC engines, of course, there is a significant potential, as we have seen, like with the low numbers in bioenergy for overall renewable energy share. It has a considerable potential to be sustainable energy source for mobile and stationary applications, where biogas, of course, could be upgraded to biomethane for transportation applications. Advantages of biogas: it's a low carbon footprint, where waste volume reduction eliminates the methane emission from natural degradation. All these advantages, but there comes a lot of disadvantages also. And you see like the fuel combustion variations in gas production from place to place and time to time. and then high amount of CO2. All these limitations actually end up in reducing the operating range of the engine. So if you'll see some plots here, this clearly shows that this is with respect to the OB index. So biogas typically you would say like 40% CO2. So if we see this plot, this is 40% CO2, OB index is around 20. So the operating range with biogas is quite narrow. And if we get to the pure methane situation, this is the operating range. So all these limitations actually bring your operating range to be narrow, and then we have to find solutions to increase that. So overall, we can try to mitigate these disadvantages and make it workable for electricity purposes and other things. I'm not going in much details over here. Okay, so this plot says there's slide. Okay, so I think one of the ways to improve engine characteristics using variable compression ratios. So if you will see over here, you could see that if the compression ratio is increased, going from all the way typical 9 and around in gasoline engines, you could see that the operating range is very close to the methane case. So we can certainly do some engine modifications as varying the compression ratio. We could also get into variable ball actuation system. We are also working on that side. So that could also help in mitigating these limitations. Another way is, of course, the biogas upgradation. This is the plots for COB of IMEP, and if you'll, these are IMEP variation with respect to the cycles, and you could see that over this is for pure methane, and this is for typical biogas. You see a lot of variations, and then a better compromise going all the way biogas to methane. Is there is a compromise, like you can remove 20% CO2 and then get the similar characteristics as you are seeing roughly here. So this shows like there's a balance between upgradation cost and engine characteristics that can be met there. And then there is improved engine characteristics with the hydrogen emission. Of course, fuel quality can be improved. And this is a plot that shows these are the experiments that we have conducted, particularly at the lower load, because at the higher load we are good with the biogas by itself. That can even get to the higher operating limit at the higher load. At the low load, if you see, we are limited to 6 Nm here on our particular engine. And then if we get hydrogen addition a small amount, we can basically get to quite to the known load limit, that is 0.8 Newton meter. So there are quite of some interesting ways to extend the operating range. With that, I'll conclude and tell that biogas is an attractive replacement for conventional fuels for engines and heat generation applications. Of course, there are limitations which can be improved through engine modifications and fuel quality improvement, along with a small quantity of hydrogen. Hydrogen can also come as a green hydrogen, which will be supportive to that. So some future pathways is development of efficient biogas operation techniques, because those are limiting factors as well. And then some specific engine modifications are needed for making these engines to be more feasible for power generation purposes. Thank you.
Thank you. So now we'll open the floor for questions in the panelists in our panel discussion. Any questions?
Hi, I would like to thank all the speakers for the very nice talks. I am Anil from IIT Goa. I have a question for Professor Kohle, mostly out of curiosity. Why lemon peel oil?
Why not lemon peel oil?
If we can use energy to...
we can basically use 60% of essentially renewable fuel. Okay, so you are basically reducing the dependence on conventional fuel, so why not lemon peel oil?
No. For example, if we look at ethanol, we know that there is a large source of ethanol available.
Ethanol, you cannot exceed 20%.
Agree? No. Again, is enough lemon peel oil available?
Yes. See, essentially this research is going to basically give the impetus to go towards that. Okay, so reducing the cost as well as reducing, it's a doable thing. Okay, it's not like lemon peel oil is not producing punch. Okay, you can.
It can be.
It can be.
Okay. And you said it requires steam distillation itself?
No, that's essentially the lemon peel oil production. I am worried about the utilization. Production guys will worry about it. Utilization, I have demonstrated 60% can be used.
Yeah.
So 60% conventional fuel you can basically save.
Right.
Correct?
Yeah.
That you cannot save for any SI engine.
Yes. Again, extending my question. You mentioned some other countries also have alternative drop-in fuels. Brazil, I'm sure you know, they use a lot of ethanol all the way to E100 also, right?
See, when you talk about drop-in fuel, this is the misconception. When you are saying 100% ethanol, okay, so you are saying that ethanol is matching all the basically properties, the thermophysical as well as the commercial properties. So it's not drop-in fuel. So please do not use drop-in fuel for ethanol. It's not a drop-in fuel. It's having a very significantly different calorific value, significantly different essentially air to fuel ratio. So the dynamics changes. Okay, so it's not a drop-in fuel. So you will have to basically do some engine modification. Drop-in fuel is the one where you do not need to do any engine modification.
Understood. Okay, thank you.
The question is Professor Pankaj. I could not find a few things which the young man is asking. Can you give me a data regarding raw material for this particular oil?
For lemon peel oil production?
Not data for raw material, because see, the way you answered, I could not understand. See, instead, if you ask me to prepare biodiesel,
okay, so just a simple question. So, is lemon available all over India?
Let me complete, please. Biodiesel is an established fuel.
Yes.
Like there are plants which can produce, pilot plants which can produce 5 liters, 10 liters, 1 kiloliter as well. But then its supply is a great problem. We do not have enough biodiesel. We do not have feedstock. Biodiesel, when we talk about biodiesel, it's basically feedstock which is not available with us. Same thing, I think, is a great problem when we talk of this particular thing. There could have been millions of feedstock plants because these contain some of the oils. So why this particular wheel? And then this steel is available in a particular part of the country. Not, it is not available throughout India. I mean,
see, it's actually produced from the waste. You know, the lemon basically you just use the juice and you throw out the lemon rind, correct? So the same thing for all the cycle family that you can do. Okay, it's not just restricted to the lemon. Okay, I can do the orange peel oil. It will have basically very similar characteristics. So all the cycle family, okay, that is basically can be used for doing this kind of production. Okay, and the most important thing is essentially the replacement of what is the percentage utilization, which basically other fuel you are replacing 60%. In fact, I can tell you we can replace it with 100%.
But where from do you break that much of oil?
No, see, essentially the need will basically drive the things. Okay. Now, if it is not known, how many of you here knew that lemon fuel oil needs to be used? Okay. So first thing is awareness. Okay. Unless until you do the awareness, these things are not going to come. And cycle family is not just that it's about the lemon. Correct. And people.
That's correct. It may be alright for but the young man is asking, my question goes.
No, your question is essentially about how much is available. Okay, I don't know about how much available, but creating the awareness is my focus. Okay, because I am not worried about production.
Thank you. I want to answer. That is actually that's a good concern, and I think as we are all aware about biodiesel concerns, usage in India primarily cannot be coming from medical sources. Right? So of course there is a limitation, and it has to be taken care in the future accordingly. Because if we see biodiesel, is also like because of the ethical concerns. It is basically out of some context now.
But this is only from the peel. We don't basically use the lemon. Okay, just the peel, the cover. Okay, so the wastage basically lemon. That's what basically used, and that can be done for any cycle family.
So I have a question for Professor Dr. So while discussing vehicle electrification, he divided light duty and heavy duty vehicles. So is there any significant difference in this strategy for electrification of light duty and heavy duty vehicles?
Well, essentially, for heavy duty vehicles which have much larger mass and range, the battery size required is extremely large. I mean, for example, for a 36-ton truck with 400-mile range will require 1,000 kilowatt-hour battery, and that makes it extremely for environmental reasons undesirable, because the battery production will be very energy intensive. And secondly, there are other issues like the battery weight and the charging time required to charge this kind of battery and so on. And therefore, though it is technically possible, practically it might not be very desirable, in fact. Though with heavy, large trucks with short ranges, it may be possible to go to electric vehicles. But then it begs the question, how do you produce the electricity? I mean, in a place like India, for a very, very, very long time, electricity will be produced by coal, and also the batteries have to be made using renewable energy as well. So in that sense, it doesn't make any sense at all in India from a CO2 point of view or from a practical point of view. As far as aviation is concerned, it's just simply not possible. I mean, medium range jet like the A320 will require a battery which weighs about 19 times the maximum takeoff weight of the plane. So in fact, when we are talking about electrification, full electrification, batteries run completely on batteries, we are talking really about cars and vans, and in particular small cars, really. And if you go to bigger and bigger cars and bigger ranges, the advantage, I mean, whatever advantage you might have in terms of greenhouse gas emissions start disappearing, in fact. So it is definitely, there's a difference between light duty and heavy duty. Did that answer your question?
Yes, sir. Thank you.
Well, it is to do with the size of the battery required, basically.
There's a question from an online audience. In PCCI combustion, at what time do you need to inject the fuel? If one of the panelists can take that question.
So for SCCI, you can have actually premix charge compression ignition. So you can have like injection to be like in two different modes, or it could be in a split way also. Like you can have in conventional, it is very late in the compression stroke, that is around close to PDC. Here you could have like some 40-50 degrees before that, and you can also have some fuel that can come into through the manifold also, which can have some pre-mixed charge already, and then another can be used for basically like later in the compression. Yeah.
Thank you. So my question probably goes to Professor Kalghatki. Regarding this electric vehicle, most of the concerns are like local air pollution, like on-road air pollution. So electric vehicle in a better way resolve this problem. Maybe the global and the total emission is at par with the conventional vehicles. But do you want to comment on this? Because this is one of the advantage with the electric vehicle, that the exposure is less while moving on the road. But and the power generation is happening in a centric location, like in a power plant. However, with the conventional vehicle, the emission is on the road and the people are exposed. So, do you want to comment on that?
That is a very fair point. In fact, electric vehicles will help improve local air quality where air quality is bad. Okay, but then the policy should be very clear about why you are doing this. In many countries, like certainly in the UK, the stated aim is to reduce greenhouse gas emissions. Okay, this is seen as a side, of course, a side benefit, you might say. And however, as I pointed out, going forward, if you have a particulate filter, which in the future all cars will have to meet local emission standards, the amount the particulate emissions are almost zero. From conventional vehicles. Internal combustion vehicles, I should say. And in that case, the emissions from tire wear, etc., start becoming much more important. And in that sense, electric vehicles will be much worse, because they will weigh about 25 to 30% more than conventional vehicles, and their tire wear emissions would be much worse. And in fact, we need to start considering all that if the number of electric vehicles actually grows to such an extent to displace internal combustion engines. And I think there's a general point about all these alternative technologies. There are many different reasons to go to alternative technologies, whether it is to do with local emissions, greenhouse gas emissions, or import substitutions. For example, energy security. We talked about biofuels, for example, and it's quite clear that biofuels have many environmental issues. In fact, most serious environmentalists now do not support biofuels. However, in a country like India, for instance, which wants to reduce import of oil, it might make sense for them to go to biofuels to some extent. So the point about all alternatives is they make some sense somewhere at some time. but you must not think of them as a complete solution to the entire transport problem. I mean, that's the point I want to make. And it's true. I mean, in China, for example, one of the driving forces for battery electric vehicles is what you pointed out, to reduce urban air pollution. Of course, you just transport it somewhere else, the pollution, but that's the price you pay. Does that answer your question?
Yes, sir. Thank you.
Any more questions?
So one more question, like as the research goes on in all dimensions with the invent of new battery technologies like aluminum air batteries, biological batteries, etc., and the use of renewable energy to generate electricity, why can't be the electrical vehicle can be an option for future?
This is
for Mr. Kalai.
I didn't quite get that, by the way. I mean, can you please repeat that? I mean, I didn't quite understand the question.
Okay. So, as the research goes on in all dimensions, with the invent of new battery technologies like aluminum air batteries, biological batteries, etc., and the use of renewable energy to generate electricity, like India has a goal of generation of 500 gigawatt energy by 2017 acre. So why can't the electric vehicle can be an option for future?
Sure. I mean, if batteries improve, if there is enough renewable energy and there is enough infrastructure, if the cost of electric vehicles upfront cost comes down, total electricity cost comes down, etc. I mean, yeah, they will automatically take more of a share. But the point about all this is it is not going to happen for a very long time, for decades to come, because the scale of the change required is immense. I mean, you know, when you say very clear, simply that India is going to install 500 gigawatts of, wind power, that means it'll probably supply about 150 effective gigawatts because of the capacity factor of wind, in fact. And there is increasing demand from all sectors for electricity. So in addition to, so you have to take the whole thing into consideration. And the scale is extremely large. For example, if you just do simple calculations, to replace, say, global aviation from with, say, run global aviation on e-fuels, you will need about 1,300 gigawatts of electricity continuously, which is equivalent to, I don't know, divided by 0.3, about 4,000 gigawatts of wind energy, for example. You know, so it is not really possible. I mean, you know, 1,300 gigawatts is about 420 nuclear power stations of the size of Hinkley Point C here, which has taken 25 years to build, you know, in this country, in the UK. So it is not going to happen very, very quickly. Of course, we must continue to look at all these options. I mean, this is the whole point about this session, I think. We have established that internal combustion engines are here to stay, and therefore we must look at every way of improving them in terms of their efficiency, in terms of finding the right fuels. But let's not kid ourselves. Let's not fool ourselves to think that this is going to replace the existing energy system very quickly. If the technology improves, it will automatically take over. I mean, as you say, if there are indeed cheaper, better batteries, it will help the spread of battery electric vehicles. But it's not on the horizon. I mean, it's not likely to happen in the next 15, 20 years. Okay? I mean, does that answer your question?
Yes, sir. Thank you.
Okay, I think with this, I would like to conclude the panel discussion. Thank you very much for the nice questions that has been raised by the audience, and my special thanks to all the panelists for giving their views on it. So now we will move to the next part of this session, which is the contributed papers by the students. So we first, all the panelists have been given this evaluation sheet, and panelists who are attending online, it has already been mailed to you. So if you can please fill in the marks for the contributed papers, and based on that, an award will be given to the person who gets the highest marks. So let's start the contributory papers, please.
Good afternoon, everyone. This is Krishnamurthy. My topic for the presentation is effect of injection strategies on combustion and emission characteristics of gasoline combustion ignition mode engine. Background and motivation. Typically, combustion ignition engines are majorly used in medium and heavy-duty automotive applications because of their higher thermal efficiency. C engines are more expensive and emits oxides of nitrogen and particulate matter emissions than spark ignition engine counterparts. COP26 concluded 100% zero-emission car and van sales from 2035. However, medium and heavy-duty vehicles will be operated by diesel fuel. So, this situation creates surplus gasoline and low refinery fuels. Hence, we need to find an engine which utilizes low refinery fuels and it able to control the harmful emissions from the engine. Methodology. GC technology utilizes low-octane gasoline in place of diesel in the combustion engine. GC technology takes the advantage of higher combustion ratio of the C engine and excellent ignition delay characteristics of gasoline. R-wind between 70 to 18 can be used for GC mode engine applications. So this figure shows the prospects of GC technology. And test conditions were given in this table. Engine load varied from 3 to 5 bar brake main effective pressure, and triple injection strategy was used for GC mode. And in case of CA mode, we used double injection strategy. So this figure shows the schematic of the injection pattern and the injection mass ratios as follows. Result and discussion. So this figure shows the in-cylinder pressure for 5 bar, 4 bar and 3 bar brake main effective pressure cases. Comparatively lower in-cylinder pressure was observed for GCI mode than CE mode conditions. So increasing the pilot injection ratio increases the in-cylinder charge homogeneity, resulting in higher in-cylinder pressure. So comparatively higher in-cylinder pressure and combustion noise was observed for advanced injection timing cases than retarded injection timing cases. So coefficient of variation of integrated mean effective pressure was higher in low engine load compared to high engine loads, and it was higher in higher pilot injection ratio cases. COV of MPRR was higher in low engine load cases than high engine load cases. Comparable thermal efficiency was observed for GCA and GC mode engine operations. Comparatively lower exhaust gas temperature was observed for GCI mode than CE mode engine operations. Comparatively higher CO and gas emissions was observed for GCI mode engine operation than baseline CE mode. Around 50% reduction in NOx and soot emissions were observed in GCI mode engine operations compared to baseline diesel conditions. Major conclusions are GCI mode engine operation with the triple injection strategy reduces the rate of pressure rise and combustion noise. Start of main injection timing strongly affects the in-cylinder combustion characteristics, and cycle-to-cycle variations were lesser in high engine loads compared to low engine load cases. Thanking you.
Any question for the presenter? One question that can be asked. Anybody from the online?
What octane number rating you are looking for? Because you said low octane number rating gasoline, right?
Yes, sir. So GC technology is able to work between R-wind between 70 to 80 in better manner. So if you choose 70, it will be good, but it will slightly increase the NOx. That's why we are focusing G8.
When you say octane number rating 70, so is it worth that calling it gasoline?
Sir, yes, sir. Here we used to blend only. So if the gasoline is higher, it probably indicates the octane.
Thank you.
Thank you, sir.
The next, so paper number 8 by Sam is not being presented. So we go to paper number 10 by Shanti Mehra.
Good afternoon, everyone. The objective of my paper is comparative study of macroscopic spray characteristics of dimethyl ether and diesel for engine application. So dimethyl ether is the ultimate next generation fuel because it can be produced from natural gas, oil residues, low-grade coal, municipal sewage waste and biomass, and also methanol. And its CJ number is also higher than diesel, so it is an excellent fuel for CI engines. And it doesn't have a carbon-carbon bond, so soot formation will be negligible. We are doing spray characteristics study because spray characteristics determine the air fuel mixing. It affects the heat release rate, the combustion, and eventually the emissions. Coming to the methodology, we use two techniques for this study: Me scattering and DBI scattering for both DME and diesel. And we also use two types of injectors for both these techniques. The experimental setup, for the experimental setup, we use this, the camshaft of the high pressure pump is coupled to the motor using a belt drive, and because DME is a gas at ambient conditions, so we used a feed pump to pressurize the fuel, and then it is again pressurized using a high pressure pump, and the fuel is then injected through the injector. And we used a white light source, the high speed camera, and the computer. Coming to the results part, so firstly the results of diesel, the Me scattering, in the Me scattering the spray penetration length was observed to be 25.26 centimeters, and I also have a video displaying the spray of diesel, and this is the evolution of spray in the DBI scattering of diesel. Now coming to the results of DME, so in the it was observed that the spray penetration length for DME was lower than that of diesel, whereas the spray plume angle was greater for DME. And here is a video showing the spray of DME. I hope it was visible. So coming to the conclusion, the spray penetration length was lesser for DME as compared to diesel because of the lesser viscosity and low density of DME. Because of lesser viscosity and low density of DME, so because of that, the ball wetting will be lesser for DME, and it will prevent the lubrication oil dilution. So if lubrication oil is burnt in the combustion chamber, then the formation, the particulate emission will be lesser, and the engine wear will also be lesser. On the contrary, the plume cone angle is greater for DME, so it is because DME is a highly dispersive fuel and it is also more volatile. So the air fuel mixing will be good for that, and the combustion would be proper. That's it. Thank you.
Quick question.
Yes.
Is there flag falling, and what are the conditions corresponding to the inside cylinder, the pressure temperatures? What is the state if you basically look at the daily at those pressure temperature conditions, whether it is gas state or liquid? Because if it is gaseous, by default it will have the low penetration length.
Sir, we have done these spray experiments at ambient conditions, and because DME has a very good atomization property, so as soon as the spray comes out of the injector, very quickly it atomizes and it forms, it converts into gaseous state. That is why the penetration length is also short of a DNA.
You are, but you would be using it for a diesel engine, isn't it?
Yes, sir, for diesel.
So the diesel pressure temperature would be much higher than the ambient. So what do you expect when you inject it? Would it be in the liquid state or would it be converted into gases? Or is it supercritical?
Sir, when we will pressurize the, means at combustion chamber conditions, the fuel will atomize because it is the property of DME, so it will be vaporized quickly. Still, the spray penetration length will be shorter for DME.
Because I think in the diesel operating conditions, you will be actually operating the supercritical regime. So if spray characteristic might be different.
Yes, sir. So we have to study that. Yes.
Thank you. Thank you. So the next paper is Deepak Kumar, paper number 15.
Good afternoon, everyone. My name is Deepak Kumar. I am an MTech student under Professor Avinash Kumar. I am working in Engine Research Laboratory at IIT Kanpur. So today I am going to talk about total cost of ownership of two-wheeler and four-wheeler in India, particularly two different states, Mumbai and Delhi. So first of all, we have to know what is TCO. So as you can see here, this is the tip of the iceberg. What we are not able to see is this, hidden things. So my point is TCO talks about all the things. TCO, whenever we go to market, we generally focus on upfront costs. We neglect the costs like operational maintenance and logistical costs. So in TCO, we will talk about all the costs and we will find the errors. So here my current objective of the present research is to calculate the TCO of two-wheeler and four-wheeler, battery electric vehicle and conventional petrol and diesel vehicle for Mumbai and Delhi. And is it achieving the cost parity before incentive or not? So in my paper, I have been using formula given by UTL, which is a published paper in energy policy, and calculator made by WR India. So this is the formula what I am using. These are the costs I am taking. After that, I am taking incentives given by state government and central government. According to central government, FAME 2 scheme, government is giving 15,000 rupees per kilowatt hour for two-wheeler, and there is no incentive for four-wheeler directly on vehicle. So I am not considering any FAME 2 incentive for four-wheeler. I am taking only state incentives. So after that, I am taking for 10 years of ownership and per day 20 km per day for two-wheelers and 35 km per day for four-wheelers as average daily distance travel. And I'm not taking any charging infrastructure cost. I'm taking same cost as we are using in our home's electricity, 6.5 rupees per kilowatt in Delhi and 8 rupees per kilowatt in Mumbai. So this is what I'm getting the result. And these are the different two-wheelers. This is battery electric vehicle and this is two-wheeler petrol. This is for Mumbai and this is for Delhi. As you can see here, when we will not include incentive, so the TCO will high. TCO of battery electric will high. It means it is more. It costs more than conventional two-wheeler petrol vehicle. But if we include, if we reduce the incentive price, then the TCO, it is achieving the cost parity. This TCO will decrease. So if you include the incentive, then it will be good. Otherwise, it is not achieving the cost parity. For four-wheeler, it is not the case. Even if you include the incentives, it is not achieving the cost parity due to the high unit cost. And as you can see here, for achieving the cost parity, you have to increase the distance. As I have taken 20 km per day, is the base. Yes. Yes, sir. So this is the result what I have found.
And for Delhi and Mumbai, the case is showing. So my conclusion is, without incentive for two-wheeler, battery electric vehicle is not achieving the cost parity, and for four-wheeler, even if incentives are included, it is not achieving the cost parity. So this is my point. Thank you.
I will compare it for, let us say, 5 years.
Yeah, I have taken 10 years.
10 years.
Yeah, total cost.
So, any incentive for, say, after 3 years battery replacement?
Yeah, I have taken to 0 replacement and 1 replacement. Two cases are there.
You find it basically.
Actually, sir, battery replacement doesn't fluctuate more. Like if you
if they basically give the incentive as a free battery replacement at the 3rd year mark.
Actually, they are giving 8-year warranty.
Yes.
Yeah. So I have taken all the things. Actually,
no,
I have.
Typically, these existing batteries they won't be reliable after 3 years. That's why I was saying that 3 years.
Actually, 100,000 kilometers they are giving the warranty. After that, they are not giving the warranty. So you have to change. So I have taken once changing the battery.
Yeah, because next time you had issue with the battery.
Yes, even all the different vehicles have the same issue. Okay.
We move to the next presentation. So we'll skip paper number 16 and go to paper number 9, Vibration Chapter.
Good afternoon, everyone. My name is Chris Chandra. I am here to present my work, prototype development of methanol.
Rasheed, can you lift your mic?
Development of spark ignited genset engine. So my objective is to investigate the combustion performance and emission and particulate characteristic of the spark ignited genset engine, which was 8.2 compression ratio and fueled with M15 and M20 fuels. So I'm using methanol. So methanol is a liquid and produces non-luminous flame after burning, and it contains higher oxygen content, and the oxygen content and hydroxyl group enhances the soot oxidation during the mixing, control, combustion and the late combustion phases. So it improves the opacity. So it has also a higher octane number, and higher octane number and oxygen content lead to the higher combustion efficiency and lower emission from the engine. So it has also higher latent heat of vaporization, which improve the volumetric efficiency and the work required for the compression of the charge. So the laminar flame speed of the methanol is also higher than the gasoline. So the advantage of the methanol economy is that it can be adopted in spark ignited engine with minimum modification in the engine. So for the methanol, I modified the engine exhaust manifold and the fuel supply system for and the vibration isolation. So, and I used the instrument for the measurement of the data, AMDS emission analyzer, and the EACH and the FTIS system for the unregulated emission. So in relevant discussion, I investigated the 3 loads: low load, medium load, and high load. So at high load, medium high, there is a slight lower pressure for the M15 and M20, and the thermal efficiency was higher for the methanol and gasoline blend. So and the methanol in blend produces the lower particulate matter, and these results are the unregulated emission from the baseline fuel in the blends. So here AM15 shows higher methane, ethane and butadiene, isobutylene for AM15, and AM20 is slightly lower for diesel. So my conclusion is the AM15 and AM20 blend shows slightly higher thermal efficiency and lower CO and SC emission, and also produces lower particulate matter.
See, one question I have is you showed a lot of, in the previous slide, you showed several of the unregulated emissions.
Yes.
I mean, what is the effect of methane blending on these emissions? I mean, are they, any idea, are they high enough to cause concern?
The unregulated emission can cause the human health and also environment. So, like,
do you have any idea whether these level of emission are of concern to human health?
Yes, sir. So, higher exposure of some of the unregulated emission can causes the skin irritation and eye irritation also, and the long-term exposure can causes the problem in the respiratory system and even maybe death.
Is it in ppm or ppb?
It is in pp.
ppm?
Yes.
Oh, pharmacy,
right? Yes, sir. All element in pp.
Yeah, you said dual fuel engine, right? So there are two modes of fuel getting in, or it's a single, like different fuels that you have tested? Looks like different fuels.
Yes, different fuels. First one is baseline gasoline, and then we have 15 and then 20.
But your title says dual fuel. I think that says like both the fuels should go in the engine, right? Simultaneously, or like port and diesel or something. DI kind of things. So I think just look at it.
Yes.
There are three ways of doing dual fuel. One is mixing, so one basically through the inlet mode and other is purification. And third one is both giving.
Sure. Thank you. Is Mandeep Singh, paper number 82.
Respected conference committee members, greetings of the day. Today I'm going to present my research work on the reduction of NOx emissions by using the boost pressure. Basically, we are trying to vary the boost pressure and try to reduce the NOx emissions in case of CRDI engines. To achieve these conditions, we have developed this test matrix. In this test matrix, we have considered two modes, mode 1 and mode 2. These are nothing but 2000 RPM and 24 kg load and 2000 RPM 60 kg load. The default value of injection pressure and injection timing are written here, and this is the default value of boost pressure at 24 kg load, and this is the default value of boost pressure at 60 kg load. Now this is the schematic diagram of the engine which we have used to develop the relation between the boost pressure and the NOx emissions. In this we have T-map sensor. This is the temperature and manifold air pressure sensor which is connected to ECU and which is then operating the vacuum modulator and which is connected to boost pressure actuator. Basically this boost pressure, this vacuum modulator is taking the signal from air manifold sensor, and based upon its reading it gives a signal to boost pressure actuator which will open and close accordingly. Now vacuum modulator is being operated with the help of a vacuum pump which is being operated with engine alternator and then creating the vacuum inside the vacuum accumulator which is giving the vacuum to vacuum modulator to operate. Now we have various type of sensors and actuator in the system that I have listed down in this slide. And now these are the conditions where we are working. Now we can see here we have three axes. This black one is the brake thermal efficiency, this red one is the brake specific fuel consumption, and this is the exhaust gas temperature here. All these graphs are being plotted for the AB20 fuel and the AB20 fuel, and their comparison with diesel is shown here. Now these are the values for diesel and these graphs are being plotted for the diesel fuel. Now we can see the value of brake thermal efficiency at this point and the value of brake thermal efficiency at this point. So we can see that the value at here is approximately 38, which is quite higher than this value, means we are getting good result here. But similarly, we can see the value of your NOx emissions. The NOx emissions are also very high. We are talking about the mode 2, so we will see this graph. So you can see the value of NOx emissions are also quite high in comparison to this particular value. So therefore, we have considered this particular point. At this point, we have thermal efficiency of 37%, which is higher than here, but the NOx emissions are quite better than the NOx emission at corresponding to this particular point. Similarly for the CO emissions also. With this, we are getting slight increase in the NOx emission, I think, which is quite obvious because we are getting good improvement in the NOx emission. So we can see that with a slight reduction in the NOx emissions, we can get the good values for the NOx emissions and the thermal efficiency. So this is the comparison which we have plotted for various type of readings, and this is the main conclusion, that we can reduce the boost pressure and get a better thermal efficiency benefit and NOx emission benefit by this amount of percentage. So thank you.
Any questions?
Yeah, so you said reducing the boost pressure from 160 kPa to 150 reduces the NOx. So that's the observation. Can you give the explanation to it?
Yes, sir. Because when we are reducing the boost pressure, it reduces the temperature also. It reduces the insulin temperature also. That's why we are getting the lower NOx emissions there. No doubt, in comparison to the boost pressure at 160 kilopascal, we are getting a reduction in the brake thermal efficiency. But if we compare it with diesel fuel, we are getting better. For AB20 fuel, same boost pressure, we are getting lower thermal efficiency. But if we compare with diesel fuel, we are getting higher one. That is the benefit of this particular study.
Any question from the online panelists? Okay, if not, thank you, Martin.
Thank you, sir.
Next. So we'll go to the next presentation by projector number 104.
Good afternoon to all the dignitaries and participants present at the 6th SEEK. My topic of presentation is copper molybdenum mixed oxide catalyst for efficient soot oxidation in diesel emission control after treatment devices. Diesel oxidation catalysts, that is DOCs, are catalytic converters designed specifically for diesel engines and equipment to reduce carbon monoxide, hydrocarbons, particulate matter emissions from diesel engine. Figure 1 schematically represents the DOC and DPF working in diesel engine exhaust. In here, the catalytic converter consists of a monolith honeycomb substrate coated commercially with platinum group metals or mixed metal oxide of comparable efficiency, cased in stainless steel container. The honeycomb structure of DOCs with many small parallel channels present a high catalytic contact area to exhaust gases. The exhaust pollutant upon topic of presentation is copper molybdenum mixed oxide catalyst for efficient soot oxidation in diesel emission control after treatment devices. Diesel oxidation catalysts, that is DOCs, are catalytic converters designed specifically for diesel engines and equipment to reduce carbon monoxide, hydrocarbons, particulate matter emissions from diesel engine. Figure 1 schematically represents the DOC and DPF working in diesel engine exhaust. In here, the catalytic converter consists of a monolith honeycomb substrate coated commercially with platinum group metals or mixed metal oxide of comparable efficiency, cased in stainless steel container. The honeycomb structure of DOCs with many small parallel channels present a high catalytic contact area to exhaust gases. The exhaust pollutant upon contact with the coated catalyst are oxidized and converted to less harmful components. The DOC is retrofitted in the diesel engine devices with diesel particulate filter, that is TPF, to capture particulate matter and their conversion. The abundance of platinum group metal is limited in the Earth's crust, and they are also expensive to use in DOCs. Despite these limitations, they are used extensively because of their superior oxidation capacity. Recent attempts have been to reduce the amount of PGM catalyst used in DOC or to compose catalyst having comparable efficiency with that of the PGM-based catalyst. In the present study, we have attempted to use copper and molybdenum-based oxygen-deficient catalyst for efficient soot oxidation. Copper-molybdenum mixed oxide is prepared by simple co-precipitation method and impregnated with 5% silver and potassium. The prepared compound was characterized with XRD, where highly oxygen-deficient structure of copper-molybdenum perovskite was observed from reticle refinement. The compound structure has orthorhombic unit cell with the given lattice parameters in figure 2. The catalyst was also found thermally stable up to 650 to 700 degrees Celsius, which is well above the engine exhaust temperature. SEM and TEM micrographs of the catalyst was also obtained to observe structural morphology of the prepared material. The soot oxidation performance of catalyst was tested on the TJ analyzer under atmospheric pressure in airflow, where model diesel soot was carbon black obtained from Tecusa under tight contact mode. CO2 evolved was also recorded using the attached CO2 analyzer facility. Both TJ curves and CO2 evaluation graph shows that the peak soot oxidation temperature, that is Tmax for copper molybdenum catalyst, is at 376 degrees Celsius, and that of potassium and silver promoted is at 349 and 351 degrees Celsius respectively, as can also be observed from the CO2 evolution graph. All the catalysts have Tmax below 400 degrees Celsius. The TPO profile of copper molybdenum catalyst was obtained at low oxygen content, that is, at 5% oxygen, where Tmax was observed at 338 degrees Celsius. Also, the lower Tmax observed in the TPO study compared to the previous study was due to the lower ramp rate. The repeat cycle experiments for CM1 and CM2 up to 10 number of cycles were performed, which shows highly reproducible catalytic activity confined in narrow temperature range of approximately 18 degrees Celsius. The real-time engine evaluation tests were also performed, where DOC is retrofitted with TPF. The exhaust gases were analyzed for carbon monoxide, hydrocarbon, particulate matter, and NOx evaluation. As observed from the figure, when only DOC is used, 44% carbon monoxide, 23% hydrocarbon, and 27% PM were reduced, while DOC, when fitted with TPF, 87% of carbon monoxide, 72% of hydrocarbon, and 77% of particulate matter reduction was observed. Below are the DOC and DPF dimensions given used in engine evaluation even at lower oxygen concentration. Thank you.
Okay. One question from my side. I mean, what are the potential challenges with this particular catalyst? Because one thing I saw that your CO2 conversion peaks at a very narrow temperature. Would that be a concern while using this as a catalyst for tailpipe emission?
Sir, this is the narrow temperature range that we have observed is to our advantage, I guess, because since the carbon monoxide, that is PM or CO, are oxidized in such a narrow temperature range, so they are oxidized immediately. But one of the concern regarding this may be the deposition of carbon soot, as well as the unburned nature of some of the particulate matters, because in the real diesel engine, tight contact mode of the soot is always not observed, and we have performed experiments mainly in tight contact mode. So in the real engine environment, the condition is in between the loose contact and tight contact mode, so that may be a challenge.
So now we go to the last contributory paper in this section by Mr. Nikhil Matthew.
Greetings to one and all. I am Nikhil Matthew, an MS by Research Scholar from IIT Mandi, and working under the guidance of Dr. Atul Dar. The topic of my presentation today would be the effect of exhaust heat recovered on onboard generation of HHO gas and its implication on the constituent emissions from a diesel engine. So the background would be that ICE engines have played a very vital role as the most favored prime mover and helped the world to reach where it is today. And diesel engines of the two are the most efficient, have higher mileage, and also use a cheaper fuel. But on the downside, they also are the most polluting in the lot, with a significant amount of particulate matter and HCA emissions. So our methodology or our aim is to basically reduce the particulate matter emissions or make diesel engines cleaner. So the use of HHO gas as an auxiliary fuel has been studied and known to reduce particulate matter emissions. Therefore, we decided not to use or store HHO gas to produce it on a moving vehicle without using the power from the IC engine. And so we decided to use the exhaust heat, recover power from it, and produce hydrogen on board. And by this, we can save on the storage and also have better safety. And the exhaust heat recovery part was achieved using thermoelectric generators. So the results from this are that a significant amount of total hydrocarbon and particulate matter emissions were noted specifically at higher loads. So the engine was operated at 1500 RPM for different loads, and we could produce about 44.8 watt of power at the highest load of 45 Newton meter and about 585 ml per minute of HHO. And hydrocarbon, carbon monoxide, and particulate matter emissions reduced significantly at 35.8, 28.72, and 80.52% respectively. But on the downside, we saw an increase in nitrous oxide and carbon dioxide emissions, which are a result of better or more complete combustion, which is in a way good. So the nitrous oxide emissions can be treated in the after treatment path, and CO2 is by far the best emission we can have out of a diesel engine. So we conclude that the use of HHO as an auxiliary fuel with onboard exhaust generation using exhaust heat recovery is a viable option. Thank you.
Thank you, Nikhil. Any question for the presenter from the online? Oh, he's not. Oh, he's not. He's not available for option. Okay, with that, we will end this session. Thank you to all the panelists
Thank you, sir. So with this is the end of this session. Now I would like to thank all my panelists and the moderator of this session. So I would like to invite Professor Rasheed to honor the panelists and the moderator of this session. And I would like to also thank all the panelists who have joined this session virtually. So, first I would like to invite Dr. Mayank Mittal.
Bye. Bro.
Thank you, man.
Dr. Pankaj Escole.
Thank you, Pankaj.
And the moderator of this session, Professor Rasheed.
Thank you, Professor. Big clap.
And I would like to thank all the panelists.
Yeah, thank you, dear friends, Professor Kalgatti, Professor Antonio, Professor Bay, Professor Moria, for your time and effort. We really appreciate your participation and sharing your knowledge with all of us. I really appreciate, and I hope that next time you are able to come physically to India in our next version of our conference, and we will get an opportunity to honor you in person. Thank you so much, sir.
So within this is the end of this session. So we have the IT aspect outside, and then we are going to start the award function ceremony.